Hello everyone. Okay, so we'll wait till 10:30 and we'll start. I guess we can start now. So we'll discuss the first five problems of Dip 2, today's starters Dip 2. Let's start with the first one. So this is the question. You are given a string S of length n, denoting the current state of the banner uh, to maintain visually uniformity. To maintain visual uniformity, the design teams allow the following two types of transformations. Operation one is that you may convert any uppercase letter to its corresponding lowercase letter for any index. SI, convert it to the corresponding lowercase letter. Yeah. And operation two is you may choose exactly one lowercase letter and convert all of its occurrences into another lowercase letter. So, first of all, let's understand the question. So, question one. We have a string S of length n, where we have some characters, n characters, which can be uppercase or lowercase both. Um, and operation one is that we can convert any uppercase letter to a lowercase letter only. So suppose we have some letters capital A, small a, then capital B, capital C, and small c, and capital D. That's what we have. We can convert any uppercase letter to the corresponding small case letter for operation one, and we can perform this operation any number of times. Operation two is we can convert exactly one lowercase letter, all of the occurrences of any one lowercase letter to any other lowercase letter. Um, this is the example is given here. For example, in this one only, um, we can convert. Suppose we first converted these uppercase letters to lowercase letters, then we can convert. Suppose we choose C, we can convert C into any other lowercase English letter. For example, we convert it to D. So it will be A capital B, 3 small d, and then small d, capital D. I hope the operations are clear. The second operation we can perform only once. And now our objective is to, the score of the banner is defined to be the maximum number of occurrences of any single lowercase letter present in it. For example, this is the and we need to find the maximum possible score the banner can attain by performing the above operations, where the second operation can be performed only once. Okay. So first of all, one thing we need to notice here is that we need to maximize the number of occurrences of a single lowercase letter. So if any letter is uppercase, we don't need it. So we will simply convert all of the uppercase letters to lowercase letters because uppercase letters are simply not required. In the second operation, also you need to convert any lowercase letter to any other lowercase letter. So in the string, all of the uppercase letters that we have, we will first of all convert it to lowercase letters because uppercase letters are not required in our answer. And then and this was operation one, and we can perform it any number of times, so that's not an issue. Now for operation two, we can choose any one lowercase letter and convert all of its occurrences to any other lowercase letter. And we need to find the maximum number of occurrences of any single lowercase letter. So after doing this operation one several number of times, we will get a string of all lowercase English alphabets. After this, if we do not perform the second operation, if we do not need to perform the second operation, the answer will be simply the maximum count of any single lowercase letter after performing the operation one. So we will first of all simply count the frequency of all the lowercase English letters. So for A, the frequency is 2 here. For B, the frequency is 1 here. For D, the frequency is 3. For C, frequency is 0. And for all other lowercase letters, the frequency is 0. So if we were not allowed to perform operation 2, then the answer would be simply D. The answer would be simply 3 here. Um, yeah. But now we are allowed to perform operation 2 one time. What is operation 2? We can select any character and convert all of its occurrences. Suppose we select B here and convert all of its occurrences to A. So in this case, B has only one occurrence. Suppose there was a string where B had three occurrences. So we will simply convert all the three occurrences of B to A. That's what the operation is. After this, what will happen? The occurrences of B will become 0. The occurrences of B will become 0. B will be as it is. And A will be uh, occurrences of A plus occurrences of B. And after this, we need to find the maximum among all of these numbers. So this is a simple problem where you are given an array and you need to find the maximum sum of any two numbers. So for this, we will simply take the two maximum frequencies and add them. So for like in this case, was A is equal to 2, B is 1, and B has three occurrences. So for this, there were these three numbers. We need to find two maximum numbers and then simply add them. That was 3 and 2. So the answer for this string will be 5. We can see the examples also here. Uh, A occurs two times, B also occurs two times, C and D, all of them occurs two times. And we don't need to care about this uppercase thing because we can simply convert it to lowercase using operation 1. So there are four different characters. All of them have frequency 2. So two maximum are 2 and 2, and their sum is 4. Here also, this is there is A and B. A has one frequency, B has one frequency. The sum of two maximum frequencies will be 2. Similarly, here there are two X and one Y. So the answer will be 3. So that's the logic for the first question. I don't have the code for this, but I guess we can skip the code for this particular question. Okay, so so now let's move to the second question. For the next four questions, we have the codes. So there are B boys and G girls who would like to take accommodation in a hotel. The hotel has infinitely many rooms, and each room with a positive number of occupants must satisfy the following conditions. The conditions are there should be at least X boys, there should be at least Y girls, and it can contain at most N people in total. Now we need to determine the minimum number of rooms required to accommodate all of the people, all of the children. Also, if it is not possible, then we need to output -1. Okay, so that's question two. We have B boys, we have G girls, and we have uh, some infinite number of rooms. And we need to fit all of these B plus G people in the rooms such that in any one room, there should be at least what was the variable X and Y. Yeah. There should be at least X boys, there should be at least Y girls, and there should be at most N people. So, first of all, if we consider any room, there should be at least X boys plus there should be at least Y girls. So, in total, if a room is occupied, there should be at least X plus Y people in that room, that is X boys and Y girls. So, first of all, and there should be at most N people. So, first of all, if this X plus Y is greater than N, then we simply cannot accommodate all of these people in the given amount of rooms. Because there should be X boys in the room, Y girls in the room. So yeah. If X plus Y is greater than N, we cannot give a solution to this problem. As in one room, there should be at least X boys and at least Y girls. But also, there can be at most n people in one single room. So if this condition holds true, then the answer will be -1. Now let's move ahead. Um, if this condition is not true, then we need to check if we can get an answer or not. First of all, first of all, um, what can be the minimum answer? What can be the minimum possible answer for to accommodate all of these people? The answer will be the minimum possible answer will be simply b plus v by n plus seal. We will simply fit n people in all of the rooms, in all of the possible rooms, and the last room that we have left, we will fit the remaining number of people there. So that's why it is the total number of people by n का seal. Suppose we have suppose now the question is that is it possible that we cannot accommodate the given number of people in this particular rooms, and we need some more rooms to accommodate them. Suppose this is x, v plus g by n ka floor is x, and suppose uh, the um, the actual answer is y, which is greater than x. Now we are considering this. This is not addition. We will contradict this afterwards. Y cannot be less than x because if y is less than x, then simply y into n will be less than b plus g because x is the seal of b plus g by n. So if we consider that the solution is actually y and it is greater than x, then what conditions should hold true? The conditions will be that in all of the y rooms, there should be at least, oh, sorry, I called it x, let's call it a. So there is, so it does not confuse anyone as x is already used here. So if we take y rooms, the first condition is that all of the rooms should have at least x boys. So y into x is the number of boys that we require, that is at least required. So y into x should be less than or equal to the total number of boys, that is b. Now, similarly for girls also, if we take some, let's say, what, there are y rooms, and in every room, ah shit, y is also used here. We'll call it b, I guess. Small b. No, let's call it t actually. So if we need t number of rooms, then t into x should be less than equal to b, since in every room there should be at least x boys. Similarly, in every room there should be at least y girls. And this number should also be less than equal to g, since we have only g girls available. Now, these are the two required conditions that should be met. If these conditions are true, then we can simply accommodate all of the people in y rooms. Also, it is given that y is greater than or equal to x, greater than or equal to x, as to satisfy the third condition that was only n people can accommodate in one single room. So we can simply see that for this equation to contradict t, if t becomes larger, this equation will become false for t going upwards. For t becoming larger, this equation will eventually become false. So it's best for us for t to be as less as possible, and the minimum value of t can be a. That was b plus d का floor, b plus d by n का seal. So the minimum number of possible rooms will be simply this a, that was the seal. We will check for a if it is possible to accommodate all of the people in a using this particular condition, putting t equal to a here, or granted only. If these two condition holds, then the answer is a. Otherwise, we actually cannot accommodate all of the people in the given number of rooms. If this condition is true, then the answer is a. Otherwise, the answer is minus one. As uh, to give you a visualization of this particular thing, why it is becoming minus one if this equation is not true. Let's just consider a case where let's say x is equal to 3 and y is also equal to 3. And let's say b is equal to 5, g is also equal to, let's say g is, let's say, equal to 6 only, and n is equal to 6. So first of all, in every room, there should be at least three boys and three girls. So at least six people should be there in all of the rooms that are accommodated right now. And this sum should be less than equal to n, which is true here. 3 plus 3 is less than equal to 6. This condition is true. So the answer is not instantly minus 1. Now we will check further. Now, for five boys, right? There are five boys, and we need to accommodate in them in, let's say, two rooms, such that in all of the rooms there should be at least three there should be at least three boys, and it should be less than equal to six also. So since b is 5, we can see that if we put three boys in one room, then we cannot accommodate the rest of the two in other room, because at least there should be at least three boys in one room. So for the boys to accommodate all the boys, we will need to put all the boys in the same room. That is, all the five boys will go in one room, and then for girls, there were six girls, right? And only one room is available here, and only one seat is available after the five, since n was equal to six. We can see that we cannot fit more than one girl here in this room, but there should be at least three girls in the accommodated room. So that's why it is not possible to accommodate all of the people in this given arrangement. There is the code for this thing. Mhm. As we said, if x plus y is greater than n, then the answer will be minus 1, since x and y are the minimum number of required people in one room, and n is the maximum number of allowed people in one room. And then the answer, if the answer is possible, then the answer will be b plus g by n ka seal. So this is the answer. And for the answer to be possible, we need to make sure this condition, that was b should be greater than equal to x into answer. What is x into answer? X into answer was the minimum number of boys required. Since in every room that is stored in answer, for every room there should be at least X boys in it, and for similarly here also, for every room there should be at least Y girls in it. So if these two conditions hold, then the answer is possible. Otherwise, answer is -1. I hope that's clear to everyone. Yeah. Now let's move to the next question. Let me see if there is any issue. Okay. So let us discuss the third problem of crypto. That is, there is a coin. This is a stock problem. So during this, the coding club launched a brand new virtual stock called Advitiya coin to give participants a taste of real world trading strategies. The price of the coin changes throughout the day and is recorded in an array P of size n, where Pi represents the price of the stock at any time index I. So, a participant can perform multiple trades during the day following the rules below. Um, a valid trade is one of the following. We choose an index I, which is less than J, and buy a stock at index I and sell it at index J, or uh, s- sell the stock at index I and buy the stock at index J. Both of them are possible. If a trade is made by choosing I and J, there should be no other buy or sell operation should take place between these indexes I and J, and each trade incurs at a fixed transaction cost X. Okay. If we don't consider this transaction cost, then the profit is simply the sell price minus buy price. But since there is a transaction cost, we will simply subtract it from this, and the profit will be this equation. Uh, and now we need to, the trade is considered winning if the profit is strictly positive. Okay. Now you are given an array P of length n denoting the prices of the stock at various time indexes, as well as the transaction cost. We need to compute the maximum number of winning trades that can be performed. So first of all, let's break down the question. So pretty. First of all, we are given an array P where for all the indexes, we are given a price Pi for that corresponding time index. Now, what we can do is choose any two indices. Suppose we chose some index I, suppose I is 3, and some index J. This is I, this is J. Now we can simply either we can buy the stock here and sell it here, or we can sell the stock here and buy it here. So it is simply if this element is larger, we can see that if this element is larger, we will simply sell the stock here. And if the jth element is larger, then we can buy the stock at the position J and sell it at position I. If we further try to mm, uh, simplify the problem, also, if we choose this IJ, then we cannot buy or sell any stock between this I and J. So, what does that mean? If we have some array P, then we are choosing some set of subarrays of this particular array, some set of disjoint subarrays of this particular array, right? where we are either buying at first and selling here, or selling here and buying here. Both of them are possible. So we are choosing some sub-arrays where at the endpoint we are buying and selling the stocks, right? We are buying it I and then selling it j. And since we cannot buy or sell any stock between these two indices, therefore all of these sub-arrays will be disjoint, right? Now, another thing is that there is a transaction cost, that is Q, right? So what will be the profit without the transaction cost here? Suppose this was X, this was Y, right? So if we buy the stock here and sold the stock at Y, or just we did the opposite of it, then the profit that we can gain is simply mod of X minus Y. But since there is also a transaction cost K, then we'll subtract it from here. Now what we need to do is we need to also we need to make this thing positive. Uh, that means that the difference in the end between the endpoints of a particular subarray, the difference between the endpoints of one subarray should be greater than k, right? Mod of, if we rewrite it, this will be mod of x minus y should be greater than k. The difference between the endpoints of a subarray should be greater than k. And we need to maximize these disjoint subarrays in the given array, right? Hmm. So this is a standard DP problem of this was, I guess, I heard that it was a lead code problem. There was a very similar problem in lead code. I did it in some complex manner. I did something like monotonic map stuff, but I'll tell you the easier and the basic solution of this. So I guess all of you can see that this is something. This feels like something. This feels something like DP, where we will store for every index I. We will somehow calculate that for the prefix array I, how many maximum disjoint subarrays can we make such that their difference in the endpoints is greater than k. So for this, we will simply store two DBs. The first will be sorry. uh, the first will be if we have sold. Just a second. Yeah, the DP1 will be that we have sold an element at some price pi, and now we need to buy some element to um, to uh, to close this subarray. We have opened a subarray by selling an element, and now we need to close the subarray by buying something. Similarly, DP2 will be that buyed we have brought some we have bought the stock at some index I, suppose, or you can simply store at some value pi. So now we need to sell a stock to close this subarray. These are the two DPs that we'll store. Also, yeah, we'll also store here the number of subarrays that we have already, the number of transactions that we have already made, the number of full transactions. That means buying a stock and selling a stock. So the number of full transactions, suppose that is T. the number of full transactions that we have already made, that also we will store in DP1 and DP2, right? Now, for the transitions of these two DP, when we go to some element I, let's say, we have iterated till I minus 1. Now we went to this index I where the price is Pi. We can first of all check that whether this particular element, the difference between this element and this element of this DP1, I minus 1, is greater than K or not. If it's greater than K, then we can sell the stock. So sorry, we sold here now. So we can simply buy the stock at price Pi, and in that way we can close one more subarray. So if uh, this Pi is greater than, or for all the DPs, we will store a pair Pi comma P. So if Pi was greater than DP at DP1 of I minus 1, sorry, if Pi, the difference we will simply calculate. That's better actually. If the difference between Pi and DP at DP1 of I minus 1 not first. If this thing holds true, if this thing is greater than K, the difference between Pi and the difference between the last DP's element, that's what Pi. Now that means we sold with something at Pi. If this thing is true, then we can simply close an array here, right? Close the subarray here. So in that case, what we will do is we will simply consider we will simply make P is equal to P minus 1, P plus 1, sorry. And if this thing is not true, in that case, we will check if the current Pi is less than, sorry, also it should be greater. If the current Pi is greater than the previous, this element, this one, if the current Pi is is greater than this element, then we can simply say that no, we are not selling the stock here since we have not closed this deal, right? So we are not selling the stock here. Instead, we will sell the stock at this PI, as this is as this gives us a better value. Since selling a stock at a higher price is better, right? So that's why. So we will say that this gives us a better value. So that's why we'll actually sell the stock here instead of the previous element. And if this thing is true, then of course we'll do this, closing a subarray. Similarly, for buying, we will check the same thing. Instead of DP1, it will be DP2 here. All other things are similar. If the difference between the current PI and the DP2's element is greater than K, then we can again close the subarray here and move forward. Otherwise, if this condition does not hold true for DP2 also, then what we'll do is we will check for PI again. If PI, this time, if PI is less than, if PI is less than this element, then we will say that no, we have not buy the stock at this particular element. We will buy the stock here instead, as this gives us a better value. Buying a stock for a lesser price is always better. So these are the two conditions that we will check. First of all, we will check for DP1. If we can close the subarray here, then we will simply close the subarray here and we will update the T in both the DPs. If we close a subarray at DP1 and this T becomes T plus 1, then of course it is better to say that no, DP2 is also not required now, as we have already closed a deal till here. Now we will consider opening a deal after this. So this was the overview of the idea, the actual solution, the actual intended solution of this problem, which I was not able to come up with. In time pressure, I did something very complex here. I don't think so that it would be great to explain this complex solution to you guys. This was the overview of the actual solution, actual intended solution of this problem. This was a lead code problem. You can, I guess, you guys can search for it. Okay. Now, for the next two problems, I have the actual code. Like, I guess I did it correctly, so it's not an issue for the next two problems. Okay, so let's move to the next problem, which is min max 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 min max. That is question 4 of div 2. Mm. So we are given an array A which consists of n distinct integers. Now, what we need to do is we need to rearrange the elements of A to form a new array, to form a permutation of the array given. And for this permutation, we will construct an array R, which will be the maximum of the prefix of the array P I, the ith prefix of the first I elements, the maximum of the prefix I minus the minimum of this. And now your goal is to maximize the max of this sequence. The max of the sequence is the smallest non-negative integer that does not appear in it. And now for this, there will be a maximum possible max that we can create. And for that maximum possible max, we need to find the number of distinct permutations of A. There will be n factorial permutations of A, and among that, we need to find the permutations of A that will result in this maximum possible max. Okay, so let's first of all break down the problem, and then we'll look at the approach. Okay, so we have an array A here with some elements. We need to rearrange it. We need to rearrange it such that the array R, which is given by this Ri equal to max of the first I elements of that array P minus the minimum of first I elements of the array P. So after rearranging the array, what we need to do is we need to construct an array R where Ri is equal to max of E from 1 to I minus min of P from 1 to I. Right. Now, the first thing that we can notice is suppose we have calculated ith element of this R array. For R, we have calculated the ith element. Now, we can easily prove that R of I plus 1 will always be greater than or equal to Ri. Now, how can we prove this? We can simply prove this by saying that uh, the maximum element of the maximum element of P1 to Pi will always be less than or equal to the maximum element of P1 to P of I plus 1, right? How can we say this? The maximum element of first I elements will always be there in the maximum in the first I plus 1 elements. So the new maximum will always be greater than or equal to the previous maximum, as we are adding one more element to the prefix, right? Similarly, we can say that the minimum of the first I elements will always be greater than or equal to the minimum of first I plus 1 elements. Yeah. How can we say this? The minimum of first I elements will always be there in the subarray of P1 to Pi, and we are adding Pi plus 1 also here. So the minimum will always be less than or equal to the previous minimum, right? Now, after making these two equations, am I- yeah. So after making these two equations, what we can do is we will first of all multiply minus 1 here. So this inequality will look like this now. And then we'll add both of these inequalities. So after adding these, we will simply get maximum of P1 to Pi minus minimum of P1 to Pi will always be less than or equal to maximum of P1 to Pi minus Pi plus 1. This is 1 minus minimum of the same number of elements. So what is this? This is simply Ri is less than equal to R of I plus 1. Right. Now, this is a uh, very important relation that we came up with. Ri is always less than or equal to R of I plus 1. So after seeing this, again, we had an array A, right? We will rearrange the array A into some array P, and now uh, we will we will want to maximize the max of this array R, right? So let us consider some array P1, P2, P3, P4, P5, uh, Pn, right? So what will be R1? R1, just a second, guys. Sorry. So for the array R of array P, we will get R1 is equal to 0 since there is only one element. So the maximum minus minimum will be 0. For R2, we will get something like mod of P2 minus P1, right? One of them will be maximum, one of them will be minimum. So we will get something like P2 minus P1. Now, if P2 and P1 are equal, somewhere in the array we will find an element that is that is distinct. So let's consider that for here that the first two elements are distinct only. So if this mod becomes two, or we can say if this not mod does not become one, and it becomes some element greater than or greater than one. For here, let's say this R2 becomes two. Sorry, yeah, this was R2. If R2 becomes two, R1 was zero. If R2 becomes two, then for all the elements after this, R3, R4, for all the elements after R2, all the elements will be greater than or equal to 2 because R of I plus 1 will always be greater than or equal to Rn. Right? So if R2 is 2, then R3 will be greater than or equal to 2. Let's say it's 2 only. R4 will, let's say, become 3. So if we get a difference of greater than 1 here, then in this case, the max of this particular array will be 1, right? Now, we also know that all of these elements are distinct as it was given in the question. You are given an array A consisting of n distinct integers, right? So all of these integers are distinct. So if R1 is 0, then to maximize the max, we need R2 to be 1. R2 cannot be 0 because if R2 becomes 0, then P2 and P1 will be equal, which is not the case here as all the elements are distinct. So to maximize the max, we want R2 to be 1, right? Just a second. Yep. Let's say R1 is 0, and for R2 to be 1, the difference between P2 and P1 should be 1, right? The difference between P1 and P2 should be 1. That means when we sort the array, then P1 and P2 should be adjacent elements. And now similarly, when we'll move to R3, R3 should be 2. R3 again, R3, sorry, yeah. So R3 cannot be 1 here as, yeah, it's, let's say here P1 was greater than P2. For now, let's say P1 was greater than P2 initially. So when we insert a P3, if P3 is greater than P1, right? If P3 is greater than P1, then R3 will be simply P3 minus P2. Or you can say the largest element minus the smallest element, which will be greater than or equal to 2, as the difference between these two elements is 1, right? Difference between P1 and and P2 is 1. So the difference between P3 and P2 will always be greater than or equal to 1. And we need it to be 2. So what does that mean? P3 will also be adjacent to P1. That means the difference between P1 and P3 will be 1 again. And if P3 is not greater than P1, suppose P3 is less than P2. Also, yeah, P3 cannot be between these two elements as the difference between these two elements is 1. So these two elements are adjacent elements. So P3 cannot be any distinct element between these two elements, right? Now, if we say that P3 is less than P2, then again, the R3 will become difference between P1 and P3, which will be again greater than 1. And for for the maximum possible max, we will want it to be 2, right? So P3 will be again This difference was 1. This difference is 2. So P3 will also be at a difference of 1 from P2. Now, what are we seeing here? We are seeing that the first three elements are adjacent elements, consecutive elements. First two elements were also consecutive elements. First three elements are consecutive elements for the max to be maximized. Now, R3's R1 was 0, R2 was 1, R3 has become 2. Now, for R4 to become 3, again we'll see. Of course, R4 cannot be greater than 3, as if R4 becomes greater than 3, then it will be, suppose it is 5 here. Then the R array will keep on increasing, as we saw here. R is an increasing array. So R is actually a strictly increasing array. Yeah. So R will keep on increasing. So that's why we will want R4 to be 3 to again maximize our max. Right? To maximize our max. So let us consider that the fourth element is again, if the fourth element is here, after fourth element cannot be here between P1 and P2 as these two are adjacent elements. Similarly, fourth element cannot be between P2 and P3 as these two are also adjacent elements. Let's say that fourth element comes after P1. So again, initially this difference between P3 and P1 was 3. Now this difference will increase and we want it to increase by 1 only. So what does we get from that? That if we insert a fourth element here, then its difference should be 1 from this. And its difference should be, if we don't insert it here, if the fourth element is less than P3, then again the difference will be 1 from P3 also, right? That means fourth element will also be adjacent to one of the endpoints of the first three elements. Now, what are we getting here? For the max to be maximized, we want the R to increase continuously 0, 1, 2, 3, 4. Suppose it increases up to some value x or it increases up to some Rx, right? Now, what does that signify? That the first x elements will be adjacent to each other, as we saw here. So we can say that for max to be maximized, we will, sorry, uh, so for the max to be maximized, we will put consecutive elements in the beginning of R, right? We will put consecutive elements in the beginning of R so that we will get our desired mix, and then for the rest of the elements that are not consecutive to any of these elements, we can put them in any order, that is n minus 1 ka factorial. Suppose this is x, right? So that will be n minus x ka factorial. Now, uh, as we can see in problem, first of all we need to find the maximum possible mix that we can create. What will be the maximum possible mix? The maximum possible max, we can simply find it by iterating over all the elements of array A, the array A that was initially given. We will first of all sort the array as we can rearrange it, right? And we will find the largest continuous subset of A such that all of the elements in it are adjacent. Suppose that size comes X, right? So we will arrange the first X elements of the array A in the beginning, and then for the rest, we can simply arrange them in any order, right? So, for example, let's take an example to show you guys. Let's say the array A after sorting looks like this: 1, 2, 3, 5, 6, 8, 9, 10. Okay. So, what is the maximum length of adjacent elements? 3, right? 1, 2, 3. 3 length. Here also it's the same. 8, 9, 10. 3. So the maximum possible max that we can create is 3. Right. Now we need to find the number of ways in which we can create this max. For that, first of all, of course, for the rest of the elements, we will simply multiply n minus x the factorial to our answer. For suppose there are three elements, how can we arrange them? First of all, of course, we can arrange them like 1, 2, and 3, and like 3, 2, and 1. But what we can do is we can simply start it with 2 and then add a 1 and then add a 3. Or this was called first add a 2, then add a 3, and then add a 1. What are we doing? We are taking a particular element here. Suppose that element is, let's say we have x consecutive. We have got x consecutive elements and in a sorted order, right? Um, let's call this B. This is something B1, then B2, then B3 to B, right? X is the length of this array, and all of the elements are adjacent. That means B of I plus 1 minus Bi is always equal to 1. All of these are adjacent elements, and the length of this array is 8. Now, what we need to do is we need to pick one element to start, and then what we can do is we can either go one element in the right, because we need to put adjacent elements in the starting, right? So if suppose if we put B3 here, B3 in the starting, then we can put B2 or we can put B4, right? If we put B4, then we can put B2 or we can put B5, right? Now, if you look at this, if we are starting at some index I, uh, this is a standard permutation problem where if you are starting at some index X, you will need to uh, take, suppose this is 4 here, right? You will need to take three elements from its left and x minus 4 elements from its right, right? So for any ith index in this array B, how many ways can we arrange this array for in the required order? That is, all of the starting elements will be adjacent. In how many ways can we arrange this array starting with its ith element? Suppose this is the ith element, and we have sorry, ith element it is, right? So we will have I minus 1 elements less than it, and x minus I elements greater than it, right? So this is a classic thing. You can simply say that we need to make a left and right array where there is some left and some right, and the number of lefts be exactly I minus 1, and the number of I rights should be exactly x minus I. This simply comes out to be the sum, that is x minus 1, x minus 1 c, I minus 1, right? This will be the number of ways in which we can arrange this particular array in the starting of R, starting from an index I. Now we can take the I from anything from 1 to x, right? So we will simply take its summation from I is equal to 1 to I is equal to x. Now what does this look like? X1, x minus 1 c0 plus x minus 1 c1 to x minus 1. When we put I equal to x here, it will be x minus 1 c x minus 1. Now this summation is actually 2 ki power x minus 1, nc0 plus nc1 up to ncn. It is 2 ki power n, right? This is a property of NCRs. So what was X here? X was the maximum possible max that we got, right? Through iterating over the array and finding the maximum length of consecutive elements. So let us again take this example here. 1, 2, 3, 5, 6, 8, 9. So here X was 3. X was equal to 3. X was the maximum possible max. So if we take these three consecutive elements and we put them in the beginning of our array P, then the number of ways to element these first three elements in the starting is 2 raised to the power x minus 1, where x is 3. So 2 raised to the power 3 minus 1 is the number of ways to arrange the first three elements. And the rest of the elements we can arrange in any order, as that doesn't matter. Since the we will get the desired max from here, as the difference is simply gonna be more than one. So for the first three elements, to arrange them, uh, we have number of ways, which is 2 raised to the power 3 minus 1. And for the rest five elements, we can simply say that there are 5 factorial ways to arrange them, right? So this will be the answer if we start with 1, 2, 3. But the length is 3. 8, 9, 10 are also adjacent. And the length of this particular thing is also 3. So we can start with 8, 9, 10 also in the beginning of the array. So for this thing also, we will add the same quantity. That is 2 raised to the power 3 minus 2, 3 minus 1 into 5 factorial to our answer. Right. Let's see if someone has any doubt in the chat. I don't think so. Yeah. So let me summarize it for you. For the given array that we had, we'll first of all sort the array to find the maximum possible max. What was the maximum possible max? It was the highest length of adjacent numbers, adjacent numbers occurring in the array. For here, it was 3, 1, 2, 3, three adjacent numbers, and or 8, 9, 10 also. It is also the same, right? We'll first of all find the maximum possible this thing, maximum possible max possible. And for that, what we'll need to do is we will need to put these particular elements, these three elements in the starting of the array, and the rest can be anywhere. And this also we can do in multiple possible ways if there are multiple subarrays of the same length of adjacent elements. So first of all, we will find the this thing, maximum length of the adjacent elements. Then we will find the number of subarrays of maximum length. For that, suppose the maximum is mx, which is 3 here, and the count, the number of times we can make this mx. Suppose it is 2 here, right? We will simply calculate mx using two pointers, simply using two pointers. Sorry, not using two pointers. Simply using count. If the next element is by an increment of 1, then we will increase the counter. If the next element is an increment of something higher, then what here? I guess my tab just got disconnected. Just a minute. I'll be back. Uh, just a minute, guys. I'm figuring it out. Okay, let's back. Where were we? Yeah. So first of all, we will find this max, maximum max. Then we'll find the number of subarrays. Then we'll find the maximum number of subarrays of this length. And then for that, we'll calculate the answer. The answer will be simply 2 raised to the power max minus 1 into n minus mx factorial. And this thing we are going to take count times, as there are CT number of subarrays of this same length, right? Let's look at the code. We first of all input of the array. We sorted the array. Now here we are calculating the max and also calculating the count, corresponding count for the same. Count is stored in answer, right? So if the next element is simply one more than the previous element, then we will do CT plus plus. If that's not the case and the count is bigger than max, we will update the max. Answer will also become one. If the difference between these two corresponding elements is greater than one and this count is equal to max, then we will increment the answer. As we are counting the number of subarrays that is equal to mx. Right. So we will increment the answer in this case. Otherwise, CT will be simply equal to 1. There are multiple possible ways to implement this thing, like using two pointers or using something else. I guess you guys can do it. What main thing is, the final formula that we got was 2 raised to the power mx minus 1. So mx minus 1 times I'll multiply 2 in the answer. I can simply do it in the loop as it's within the range of n. So I don't need to use the binary power function or I don't need to pre-calculate the factorials. I can simply do it in the for loop only. So that's what I did. And then we will simply multiply n minus extra factorial to it, right? That's what we did, right? This was the formula. N minus m extra factorial and 2 raised to the power mx minus 1 into 2 raised to the power mx minus 1. And for count, count was simply stored in answer only. So I hope this question is clear to everyone. Ah, okay. Now moving to the last question. Another interesting problem. This is question number 5 of the diploma. Okay. So we are given a tree with n vertices. We can walk on the tree in a sequence of vertices such that it is W1, W2, WK, such that for every two adjacent vertices, there is a edge between them, and such that there exists an edge between the vertices Wi and Wi plus 1. Also, note that the walk is allowed to repeat it to have repeated vertices. And now the walk is said to be valid if and only if we start with 1 and we end with n. So we need to walk from 1 to n. Also, if we reach n, then we need to end the walk there only. We cannot go to n and then come back to n. So that means Wi should not be equal to n for any I less than k. I that means n is the end element of the array, but we are allowed to come back to 1, right? Except at the last step. And each vertex appears at most twice in the walk. They are allowed to appear multiple times, but also at most twice, right? Uh, Now we need to count the number of valid walks in given tree. The answer can be large, so yeah. So first of all, how can I start it? How can I start explaining this question? Hmm. Okay, so first of all, let's make a tree, a random tree here, right? Uh, Suppose this is a tree where, of course, this is the first and this is the nth. Let's say we need to start with the first and we need to end at the nth. Now, what we can do is for every particular vertex, we can come to that vertex at most two times, right? So the very basic thing that we can do is simply go through these four nodes and go to n. Now, what we can also do is we can go to some other subtree of 1 that does not contain n. Suppose we go here and then we come back and then we can again go to n in the same fashion, right? Or we can also do, we can first of all go in one and then we can come back and then we can go here and then we can go here and then we can again go in this subtree and then come back and then go here. Now, how are we allowed? How are we exactly doing this? Since for every vertex, since for every vertex, we are allowed to go to it at most twice, right? So in vertex one, I can go in any one subtree, in any one subtree of this one of any children of one. I can go in any one subtree of the children of one and I can come back. So going and coming back. I have already came to one twice. Now I cannot come back at once. So I can go to a subtree of one only once, right? And then come back to one. And then head towards this node n, right? So let us see for one only how many ways can I do this? I can go to this index and then come back, or I can go to this index and then come back, right? Or for one, I can go to this index and then come back, or I can go to this index and then this index and then come back, or I can go to this index and then this index and then come back. Now, one thing that we need to focus here is the same thing that is applicable for one, it is applicable for all the indexes. So if we came at this index, suppose through iterating, if we If we went to this vertex, this vertex, and then I went to this vertex. So after going through these two vertices, I cannot go to this vertex. As for this one also, if I come back here, I have already made two occurrences in this particular vertex, so I cannot go in the subtree. If I go to its subtree, then I cannot return to one, right? So what is this effectively? This thing effectively is I can go to any vertex in the subtrees of one, but not in that subtree where n is there, right? So I can go to any subtree of one in any vertex of any of the subtree of one, and I can come back to one, right? This is the number of ways I can iterate up to one, like iterate in one. And then when we go downwards, we will simply check the same thing for more vertices. Suppose we after doing the same thing for one, then this vertex, then after that, suppose we came to this vertex. Now there are also some subtrees of this vertex. Yeah. So for this vertex also, we can simply do the same thing. To end at this vertex, we first of all came here, and then we can go to any one subtree, just like we did in one. So what exactly is this? For one, in how many ways can we end up in one? First of all, we came at one, right? Then we can choose any one vertex in its subtree, and then we can choose to iterate over that vertex and then come back. So in how many ways are we doing it? It's simply the number of nodes in the subtree of one, excluding the subtree where n was there. Correct? So it's exactly the number of nodes in the subtree, or the number of the size of the subtree, excluding the size where n was there. Where n was excluding the size of the subtree with n. So for one, what was the number of it? One, two, three, four, five, six, seven. Right. So we can go to any one node and then come back. But we can also choose not to go anywhere and just create one and proceed. So that is also counted here, since we are counting all the vertices in its subtree, right? So we are including one also. If we say that we are not going anywhere, then we are actually saying that we are at one only, right? So that's what the thing is for every vertex. We will calculate the number of vertices where we can go and come back to that vertex in its subtree, right? So if this was the only possible thing that we can do, then what will be the answer? The answer will be simply what is the simple path from one to n? It consists this one vertex, this vertex, and then this nth vertex. We will simply take the dp. What is the dp? Dp is simply again dp is the size of the subtree of the node, excluding the subtree size where n with n, right? So we can simply take the subtree size of all the nodes in the simple path from 1 to n, but excluding the subtree of n. We can simply store it in the dp, and then we can multiply it to the answer for all the indexes, for all the vertices that are in the simple path from 1 to n. But that's not the only case. One more thing that we can do is we can go from 1 to 2 and then come back and then head forward. What is this? We are initially we were at 1, we went to 2, we came back to 1. So for 2, we went to 2 one time. We have went to 1 time. Now then we will come back to 2. So at 1 we were 2 times. At 2 also we were there two times. And now we will head back in the downward direction. Uh, right? This is another thing that we can do. Now, how can we Consider this and so this also in our answer. Uh, can we do this for multiple edges, for multiple vertices, like heading downwards three times and then coming back? Can we do it? Let's see. If we start with one, and when then we come to two, and then we come to three, and then we go back to two, and then we come back to one. If we do this, then we cannot go back to two. Why? Because when we went down, we went to two one times. When we came up, we went to two another time. So now we cannot go to two again, right? So that means the one last thing that we can do is hit any vertex. We can go down one time, we can come up, and then again we can go down, and then continue from here, right? So what are we doing exactly? For any node I, what was our DP? Our DP was simply it stored the number of uh, the number of nodes in its subtree, excluding the subtree with n. Right now, what one more thing we can do is how can we proceed with this node? We can simply we came to this from its parent, right? We came to it. We went back to its parent. We came back here, and now we are heading forward. This is again one thing. So, what is this exactly? For this, we will store a DP. For this, we will store a DP where DP of any vertex will store coming down to it and then heading forward. Somehow coming to it in one time or in two times and then heading forward. In how many ways can we do this? That will be our DP. So for one, the DP will be simply this subtree size, excluding the subtree of n, right? But for the next nodes, let's say for three, what we can do is either we can go to that subtree thing, either we can do that, or what we can do is we can go back to its parent and then come back. Now, if we do this, if we go back to its parent, we cannot do the subtree thing for its parent also. So we can simply do that in DP. We will first of all store the path from 1 to n, the simple path from 1 to n. Here, let's say these are the nodes for the simple path from 1 to n, a1, a2, a3, dot, 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 up to an, where a1 is 1 and an is n. And this is the simple path from 1 to n. First of all, we will store this and then we will calculate dp for all of the nodes. For one, the dp will be simply the subtree size thing. For two, what we can do is for two, we will see that what was the dp of one, in how many ways can we come to one. We will multiply it in how many ways can we come to two. For two also the same. The thing will be we can simply go to its subtrees and come back, right? For two also we can go to its subtrees and come back. So for dp2 also that will be size of two. Let's say sz. Let's say it is sz. Sz is basically the, sorry, my writing is a little bad. Tree size excluding the subtree with the node n, right? This is sz. So for A1, dp at 1 will be simply sz at 1. Now for dp at 2, what we'll do is we'll say that what we did till 1, we'll do that. And for 2, we can head to its subtrees. So it will be dp2 will be dp1 into sz of 2. Correct? Now, one more thing that we can do is we can go back to its parent and then come back. What is it? If we are at 2, we can go back to its parent and we can come back. In this case, we cannot take this SZ1, right? So what is it? Suppose there is this A0. Initially, this will be 1, right? The DP A0 will be 1, DP initialization. Yeah. So for A2, we will see that we will say that we came to A2 somehow. We came to A0 somehow. Then we went to A1. Then we went to A2. Then we came back to A1, and then we went back to A2. We somehow for every let's say for an index I. This is in the simple path index, right? So for any index I, we will say that we came to I minus 2 somehow. The number of ways of coming to I minus 2 will be stored in dp of I minus 2. And then we can head to I minus 1, then I, then again I minus 1, then again I. In this case, we cannot go to the subtree of I minus 1 or I, as we are already using its two occurrences here in this path, right? So what will be this? This will be simply dp I minus 2, this. The number of ways in which I came to I minus 2, that I will add to my dpi. So what is my final dp? dp at I is dp at I minus 1 into size of I plus dp of I minus 2. This is our dp transition. If we want to come to I somehow, what we can do is come to I minus 1 somehow, and then come to I and head to its subtree, and then come back to I, or come to I minus 2 and do this particular iteration. These are the two possible things that we can do, right? And here, this I minus 1, I minus 2, these are all in order of uh, the simple path from 1 to n, right? This was the simple path from 1 to n, where a1 was 1, a n is n. This is a simple path. So this will be our AP transition, where I is in respect to the simple path thing. And yeah, after this, we will simply output the DP at this particular node. Because when we come to this node, then there is no other option other than going to the nth node. And after we reach the nth node, our iteration is over. Our walk is over, right? Uh, Let us understand this with our code also. Yeah. So we first of all put the inputs. This is our adjacency matrix or adjacency vector. Uh, in DFS, we calculated all the DPs. Here the DP is the size and DP1 is the DP in my code. Actually, let me change the names for you. Control DP, who I will replace with, uh, or let's Z, replace all. And now for all the Z1 with DP. Nice. So we have our sizes, subtree sizes, excluding the subtree with n. We have that stored in SZ, and then we'll calculate our DP, right? So we first of all did a DFS to calculate this sizes, right? In our DFS, if the node is n, then we will simply include that node in our path. We will push back it in our path and return, right? and the size of a particular node will be 1, and then we'll add all of its children's sizes doing the DFS. So we did a DFS for IT for its children, and then we looked at if path is not empty, and then IT was a part of the path, right? If IT was part of the path, that means that means the subtree containing IT contains n. So we will not add its size to our node. In that case, we will simply check. What is check function? Check function is that does our node from in the size from 1 to n, in the simple path from 1 to n. So if our child, if one of our child had n, then we'll also have n in our subtree, right? So if any of the child had n in its subtree, we will not add its size to our size. Otherwise, we will simply add our child's size to our size, right? So that's how we calculated the size array. And if this CH is true, that means we got a child who contained n. Then we will simply push back ourselves in the path. Since our child was in the path, right? One of our child was in the path from 1 to n, then we'll also be in the path from 1 to n. So that's how we found the path, right? So now our path is sorted. I push back this path to make it one index. You can push back n or 0 or anything 1000 here. I just did it to make it one index, and then we need to reverse it, right? Since in DFS call, the last node, okay, let me show it here. Since we are calling a DFS, right? The DFS will go something like this, and then it will store this in the path, and then it will store this in the path. So all of this thing is in reverse order. So we need to reverse it, right? So that's why I first of all pushed back any temporary element in the path and then reversed it. Now our path is one indexed and in the correct order, right? So this is done. Now we will simply calculate our DP. N is that path का size. So for DPI, what is DPI? DP0 will be 1. Our initialization of the DP will be 1. For DPI was DPI minus 1 into size of the path, the size of this current element, which is stored in the path, right? So DPI was DPI minus 1 into size of the current element. And if I is greater than 1, considering this edge case for I equal to 1, we cannot go back to two spaces, right? We will simply add DPI minus 2 also in our DPA. And then we took mod and simply giving output of DPI minus 1. That was the code. I hope it is clear to everyone. And yeah, that was our div 2. That was our div 2. And that was our starters 2024 uh, discussion. Um, Thank you, everyone.